Welcome to Lesson 2, Buffering Action, video number 1, where we'll look at weak acid buffer systems and how they react. So with buffering action, a buffer solution is able to react with either H3O plus or OH ions to resist a large change in pH. And this is important in a lot of different aspects. So if you're looking at our blood in our body, how carbon dioxide travels, our blood is able to resist a large change in pH if for some reason we have acid or base added into our blood system through different mechanisms in our metabolism. And large swings in pH would be very detrimental to our health and could even make us die. So our blood acts as a buffer. So when I'm going to give very specific examples for weak acid buffer systems, but I'm going to write them in generalities using our HA and A minus. So HA is going to be the acid and A minus will be the salt ion that is common to both of them. So if we look at a weak acid buffer system, we know that we have this equation. And if we use the same example we've been looking at before, if we have sodium acetate and we have acetic acid, this is our HA, and the acetate part of this is our A minus. So we know that we have an equilibrium system, and this is what happens when you add a strong acid. So if we add a strong acid, what that is going to do is it is going to increase the H3O plus concentration in this equation. That is in turn going to cause a large left shift in our equilibrium. And since this whole thing is shifting to the left, the A minus is going to go down. So it's going to go down by a lot. So in our example up here, the acetate ion is going to decrease by a lot. And it decreases to almost 0. So as this is shifting this direction, and we're decreasing A minus, it also decreases the H3O plus concentration. So it in turn uses up what was added. So we have a large amount of A minus in there from that added salt. So that means that as we add H3O plus and it's going this direction, this amount of A minus is not really getting used up, but there's a lot of it there. So it keeps on shifting in this direction over to the left. So what we're going to look at is our net reaction, and this is what we're going to focus on for our problems. So we have our A minus reacting with H3O plus to give us our HA and water. So this is the overall reaction that we are looking at anytime we have a weak acid buffer system and we add a strong base. This is going to be a reference. So we're going to pick this equation if we have that condition. This is the salt ion, if you remember. This is our acid, and it has to be weak. This is our acid, and this comes from a strong acid that was added. If we add a strong base to a weak acid buffer system, this one's a little bit more complicated. So, if you recall back about 2 units, water self-ionizes. We get OH minus and H3O plus. This is a secondary equation or reaction that's happening in the strong base addition. We also have our HA plus H2O yields A minus plus H3O plus. So if we increase the OH minus concentration, that causes a left shift in the first equation here, and that in turn decreases both OH minus and H3O plus. Well, what happens here is, since we are decreasing the H3O plus in the secondary equation, we want to replace that. So that causes a right shift in equation 2, which in turn increases H3O plus, which reacts with OH minus to neutralize added OH minus. And I know that that sounds really confusing, but I'm not going to ask you to explain this in depth. I just want you to be able to recognize that if we have a weak acid buffer system and we add a strong base to it, the strong base is going to be used up, and then we're going to have a net reaction. So the OH minus plus our HA is going to create our A minus plus water. So this is the important thing to refer to. This right here is our acid and our weak acid. This is our added base, and this is our salt. So if we look at how we're going to use this in an equation, here's an example. So we have to know what we're adding and what type of buffer system this is. So it says that we're adding OH. So we're adding OH to a buffer solution that is acetic acid and sodium acetate. So this is a weak acid buffer system plus OH minus, or base. So this is our net reaction that we're going to go with. So the first part that we're going to do is we're going to find the original pH of the buffer system before anything is added. And we're going to use the Henderson-Hasselbalch equation. So we know that pH, we're dealing with an acid, is equal to pKa plus the log of our salt concentration over our acid concentration. So since we're dealing with acetic acid and sodium acetate, we have calculated the pKa of this before. Remember, you take the negative log of the Ka from your pink reference chart. So our pH is equal to 4.76 plus the log of the salt, sodium acetate, 0.100, over the acetic acid, 0.100. So our pH is equal to 4.76 because the log of 1 is 0. So there's the answer for our original concentration. So our second part of this problem is going to be after adding base. We're going to require an ice chart for this, but we're not going to have to solve for x. So choose the correct net reaction. Weak acid buffer system, we had two choices. If we had a strong acid or a strong base, we said that we're adding a strong base to this, so we're going to use this net reaction. So I'm just going to write this down, OH minus plus HA, in this case, it's our weak acid, yields A minus our salt plus H2O. And here we have our, let me move that up. Here we have our three categories: initial, change, and equilibrium. So initially, we have 0.0100 molar OH because we have moles in 1 liter. That's molarity. Our original concentration of acid is 0.1 molar, and our salt is 0.1 molar. We don't have to worry about water. Now, we said that it uses up all of the base. So this is going to go down by 0.100 molar. So that means that this one's going to go down by that amount, but A minus is going to increase by that amount. So at equilibrium, this is going to approach 0. HA is now going to be 0.0900 molar, and A minus is going to be 0.110. These are the values now for our HA and our A minus that we're going to put back into the Henderson-Hasselbalch equation that we used up above. So pH is equal to pKa plus the log of the salt, which is now 0.110, over our acid, which is now 0.0900 molar. And when we solve for this, we get a pH of 4.85. So the question says, how will the pH change? Well, it goes up slightly. And it should. We know that the higher you go when adding a base, the pH is going to go up, because going up the scale means that you're getting more basic. But it doesn't go up all that much. This is the end of this video. We will look in the next video at weak acid or weak base buffer systems and their reactions.